Once we have a sample space in hand, the next question is, what are the events of interest? Events in the formal theory are called measurable sets. This is a bit of a misnomer because a measure has yet to be specified. It is going to come, and we will call that a probability measure, but we will anticipate the provision of a measure and call events measurable sets, and we'll use the language interchangeably. So for us, an event is a measurable set, and what a measurable set is a particular kind of subset of the sample space, a subcollection of idealized outcomes. Now, naturally, we'll be interested in not just a single event, a single subset, but many possible conceivable events or measurable subsets. So what kinds of events are of interest to us? Well, naturally enough, we would like the entire sample space to be an event, because after all, if you perform the experiment, some outcome, some sample point emerges. We would also like to be able to take events and combine them. For example, I'd like to say this event or that event, or formally the union of two events. I would like to say this event and that event, the intersection of events. Or I would like to say not this event, the complement of events. In other words, starting with some basic events of interest to us, we would like to construct and conceive of more complex events, obtained by the ordinary set theoretic operations. Now, the simplest way to prescribe this is to pick two operations, say differences and unions, and prescribe everything in terms of them, and then all the other set theoretic operations are inherited from these. So we would like to conceive of complements of events and consider those to be new events. We would like to consider unions of events and consider those to be new events. And prudence compels us to look at not just unions of two or three or a finite number of events, but possibly a countable infinity of such unions. Now, why an infinity of operations, you might ask? Surely, in the real world, we don't deal with an infinity of operations. Now, the answer is twofold. One, prudence tells me that I should not a priori constrict my range of possibilities. We've already seen examples where in a conceivable experiment I can think of an infinite sequence of events that could be of interest. For example, we discussed in Tableau 3 the experiment where one tosses a coin repeatedly until two successive faces are the same. Now, in such an experiment, the experiment could, in principle, be carried on indefinitely without bound. In such a space, I could conceive of various events of interest. For example, the event that exactly 4 tosses were seen. Of course, this would mean that we obtained a sequence like a tail, a head, and 2 tails, or a head and a tail and 2 heads. Well, that is surely a bona fide event. I could say, well, what if 5 tosses exactly are required, or 6, or 7, or in general n tosses, where n need not have a bound. Now, if I want to construct a new event, the event that 4 or more tosses is needed, well, you'll see that this event can be constructed by taking an infinite, denumerably infinite union of the events that exactly 4 tosses were needed, or 5, or 6, and so on ad infinitum. So, prudence tells us that it would be wise for us to expand the space of possibilities to admit of a potential infinite number of set theoretic operations. Now, the moment we have something like this, it transpires by the ordinary rules of set algebra that immediately, if I have a collection of events, then I can take set differences, I can take symmetric differences, complements, unions and intersections in any order whatsoever, and do a countably infinite number of them and still get events. The collection of all such conceivable, measurable subsets or events is what we'll call the algebra of events. And we will denote it by the stylized uppercase script letter F. Now, when you say an algebra, we use the term advisedly. We can do things like unions, which stand in the role of addition. We can do things like intersections, which stand in the role of multiplication. This is beginning to look like an ordinary algebra. If it walks like a duck, if it quacks like a duck, well, it's got to be a duck. If it adds like an algebra, if it multiplies like an algebra, then manifestly it is an algebra, and we will, without further ado, call it an algebra. Now, formally, because we are allowing not just a finite number of operations, but a countably infinite number of operations in principle, it transpires that what we are looking at is, you could think of it as an algebra on steroids. It allows an infinity of operations. Formally, such structures are called sigma algebras, the lowercase Greek letter sigma, drawn from the German Summe, standing for really a countable number of operations like addition. Now, this is all very abstract, and of course, with the next tableau, we'll start putting some color and some rich structure around this in the form of applications. But while we are building structure, it is wise and useful to add colloquial language to the picture so that we can picture things easily, add color to it, see it in a comfortable light. So, here's some notation and language which makes this abstract picture perhaps a little more palatable. Right. We'll begin, of course, with the idea of subsets of the sample space. So we have an underlying abstract sample space, omega, on which everything is going to happen. In such a sample space, I'm going to pick subsets of interest. These are the events. We will use, generally speaking, though again we will not slavishly adhere to convention if it is wiser to switch, but in general we will use uppercase Latin letters at the low end of the alphabet, A, B, C, D, etc., to denote different possible events. And of course, in such settings, it is frequently useful to draw a picture. A Venn diagram can help us visualize interrelationships between these sets. Excellent. Now, when one performs an experiment, some outcome, little omega, transpires. This is a sample point. That little omega could be inside some set of interest to us, an event of interest to us. If that is the case, we are imagining this chance experiment being performed. It's a thought experiment, a Gedanken experiment. If an outcome of this set arises from the experiment, then we will very naturally say that this event occurs. Very colloquial language, but it just means the collection of sample points which comprise that set A, which is the event under consideration. Now, of course, if one does the experiment, some sample point or the other will happen. And therefore, the space itself, omega, is what we will call the certain event. The performance of the experiment will result in some little omega, but little omega is manifestly an element of big omega by definition, and therefore big omega occurs. It is certain to occur. By the same token, in an informal vein, we will talk about the empty set as the impossible event, because the empty set has got no elements, and so no outcome of the experiment can possibly lie in the empty set. Now, to go a little bit further, let's take a look at interactions between sets and between events. Suppose A and B are two events of interest to us and represented schematically in the Venn diagram, And suppose A and B share no elements. The intersection of A and B is empty. A and B are disjoint. In such cases, we will say colloquially that A and B are mutually exclusive. The idea here, of course, again is very, very visual, is that if one conceives of performing the experiment and an outcome omega transpires, if omega is in A, then it cannot be in B because the sets are disjoint. Likewise, if it is in B, then it cannot possibly be in A, again because the sets are disjoint. And therefore, the occurrence of the events are mutually exclusive. And we'll use the words mutually exclusive on occasion as a synonym for a disjoint pair of sets. And now finally, of course, we can, for general events A and B, we can conceive of forming their unions. We will call, in colloquial language, a union is a disjunction, an or, and we will say A or B. We can conceive of the intersection of these two events. In colloquial language, we will say the conjunction of A and B. And given an event A, we can conceive of its negation, its complement, and we will simply say not A.